tension, normal reaction, weight, and friction. Okay, now let's start with this. First of all, what are forces? Force is a vector quantity. Vector quantity is something that has both magnitude and direction. So whenever we describe a force, it needs to have both magnitude and direction. Unit for force is Newton. Now, first of all, let's consider this example. Let's say we have a block like this. If we have a force acting towards right side, that's 8 Newton, towards left side, that's 5 Newton. And we have to find the resultant of this. That's fairly straightforward because both of them are acting parallel to each other. We can just subtract the two. We can say 8 minus 5, that's the resultant for, that's 3 Newton. If it's vertical in this case as well, it's pretty straightforward. You just do 21 minus 15, and that gives you 6 Newton in the upwards direction. That's the resultant force that you've got. However, when you have forces acting in different directions, for example, if you have one force acting in the horizontal direction like this, 8 Newton, one force acting in the vertical direction like this, how do you find the resultant of a set of forces that looks like this? Now, for this, when you have forces acting perpendicular to each other, what you can do is you can make a right angle triangle, use the head to tail rule, and you say, okay, if this is the base, this is the perpendicular, then this hypotenuse is going to be the resultant force. You can find the magnitude of that resultant using Pythagoras, and that turns out to be 10 Newton in this case. But now, since force is a vector quantity, we also need direction for that. Direction means at what angle is the force acting? How do you find that direction? You can use tan for that. In this case, you can say perpendicular over the base 6/8. That should equal tan of this theta. And that will give you the angle. The angle turns out to be 36.9 degrees. So then you say the resultant force here, it's acting at an angle of 36.9 degrees above the positive x-axis, and its magnitude is 10 Newton. So whenever you write down a force, unless they specifically ask you just for the magnitude, you should also tell the direction in which it is acting, right? In this case, when you have resultant force, you will say it's 10 Newton acting at an angle of 36.9 degrees above the positive x-axis. Now, how do you describe this? How do you do this description like this? So there are 4 possibilities. You could have forces acting in these 4 different directions, as in the first quadrant, in the second quadrant, in the third quadrant, or in the fourth quadrant, right? You'll have forces acting in one of these directions. How would you describe each of them? You need to know this. For example, if you have a force acting here, 35 degrees, how would you describe this force? You look at the starting point of the force. The starting point of the force is this. We consider that the origin. Starting point is considered the origin. From that, you say, this is the positive x-axis, and the left side is the negative x-axis. So when you describe, you would either say it's above the positive x-axis or below the positive x-axis. For example, this 35 degrees, you would say it's 35 degrees above positive x-axis. If you had force acting in this direction, 40 degrees, if that's 40 degrees, that means that this angle is 50 degrees. So description of this force, the green one, that would be that it's acting 50 degrees above the negative x-axis. The left side is considered negative x-axis. Similarly, if you had this force acting in this direction, you would say it's 30 degrees below the negative x-axis. And this, you can say, this angle, since that is 80 degrees, this is 80 degrees below the positive x-axis. So that's how you would describe forces acting in these different directions. You say, what you write down what the angle is, and then you write down whether it's above or below positive or negative x-axis. Okay, that's the description that I would recommend. You can also use anti-clockwise, clockwise, but some people end up getting confused with that. This is a very easy description. Angle, positive, negative, and above or below x-axis. Okay. Now, we talked about how to find resultant of 2 forces that are acting at right angle to each other. We can just make a right angle triangle from that and find the hypotenuse. However, what if we have forces acting in some random directions like this? How do you find the resultant of this set of forces? Now, for this, we need to do something that we call resolving forces. Since we know how to find resultant of forces that are perpendicular to each other, what we try to do is we convert these forces in a form such that the forces are only horizontal and vertical. Now, since it's a vector quantity, the force is a vector quantity. We can say this 40 Newton force, that's the same thing as saying that you go this much in the horizontal direction and this much in the vertical direction. So you can break it into 2 parts like this. These are called components of this 40 Newton force. And this process is called resolving forces. Now, how do we resolve any force? For example, if we have that force 40 Newton, we can say it has two components, one acting in the horizontal direction like this, and one acting in the vertical direction like this. That 40 Newton force is equivalent to saying we've got one force acting in this direction, another force acting in this direction. This combination is equivalent to that 40 Newton. So we can break it down like this. Now, how do you find the values of these horizontal and vertical components? We have this right angle triangle. We know the angle. The angle is 30 degrees here. We can use sine and cos to figure out what these values are going to be. So for example, if we say the horizontal component is x, x over 40 becomes cos 30. And the vertical component, if that's y, y over 40 becomes sine 30. And that gives us that the horizontal component is supposed to be 40 cos 30, and the vertical component is going to be 40 sine 30. So the component that is adjacent to the angle, that will have cos with it. The component that's on the other side of the angle, that is going to have sine with it, right? Using those trigonometric functions. Now, I will be resolving these forces in a slightly different way, as in it's the same thing, it's the same logic behind it. But since in diagrams, you have a lot of forces acting a lot of times, for example, in this case, we've got 3 forces. You could have another force here that acts in this direction. Then making all of those triangles becomes makes a lot of clutter on your diagram. So for example, in this case, if you had these forces, you'll have a triangle here, you'll have another triangle here, you have another triangle here, you have another triangle here, and that ends up making you do careless errors sometimes. There's another way that I'll be using, and that is, we say, if this is the force 40 Newton that's acting in this direction, that 40 Newton is supposed to have 2 components, one acting towards the right side, one acting in the upwards direction, right? So we, instead of representing this vertical component here, we could do that. That's perfectly okay as well. I'm just representing that here at the point where the force starts. So I'll be representing the components in the rest of the session like this. Wherever the force is starting from, we make 2 components starting from that point. So one towards right side here, one upwards direction in this case. So one component will always be on one side of the force, and the other component will be on the other side of the force. And both of them will be making acute angles like this. Now, what are the components going to be now? What are the components going to be? If this is 40 Newton, and we know that the angle here is 30 degrees with the horizontal, the component that is adjacent to the angle, that will have cos with it. The component that's on the other side of the angle, that will have sine with it. Now, these are equivalent to, if we were to use this angle 60 degrees, in that case, we would say the vertical component is 40 cos 60, and the horizontal component is 40 sine 60. Right? These two are equivalent. Sine 30 is the same as cos 60. Sine 60 is the same as cos 30. We could do it both ways. So in general, we could do something like this. If we have a force like this, a force F, it has 2 components, one acting in this direction, the other acting in this direction. The component that is adjacent to the angle, that will have cos with it. And the component that's on the other side of the angle, that's going to have sine with it. Okay. If you have something like this, for instance, if this is the angle that you're using, you would say the force is acting in this direction. Now, you will be resolving the force like this. You would say you've got one component acting on one side of that force, the other acting on the other side of the force, such that they're at 90 degrees with each other. The component that has side of the angle. So that's how you'll be resolving these forces. When you have an inclined surface like this, in an inclined surface, so generally what we do is if we have no surface involved, or if we have a horizontal surface involved, what we do is we resolve forces in horizontal and vertical directions. However, when we have an inclined surface, that looks like this, we resolve forces along the surface and perpendicular to the surface. These are the 2 directions in which we resolve these components. So how are we going to resolve them? Let me show that to you here, because this is like foundation of mechanics. So if you're given that this angle, for example, is theta, this is 60 Newton force, this angle is 30 degrees. So what about 60 Newton force, first of all? We are going to resolve in these 2 directions. So what are the components of 60 going to be? One component is going to be towards the right side, the other in this direction. The component that's adjacent to the angle, that's going to have 60 cos theta. And the component on the other side of the angle, that's going to be 60 sine 30. Now, this is very important. Whenever you have a force acting in vertically downward direction, generally you'll have weight acting vertically downwards. This is very important when you're resolving forces. It will come up again and again. If the angle of the plane is theta, for instance, if the angle of the plane is theta, the components of weight, what are they going to be? If this is the direction of weight, that's always the direction of weight, vertically downwards. If the angle is theta here, that means, what is this angle going to be? This angle is going to be 90 minus theta, right? Because this is 90. If this is theta, this is 90 minus theta. And if that is 90 minus theta, then this angle here, that turns out to be theta. So in a diagram like this, these two angles are always going to be equal to each other. If this angle is theta, this angle here is also going to be theta. So what are the components of weight going to be? The components of weight on an inclined surface, they will always be like this. Along the plane, you would have sine theta. So this would be 80 sine theta. And perpendicular to the plane, you would have cos. So it will be 80 cos theta in this direction. Okay, so that's how the components are going to be look like for this weight. Okay. All right, so that's how we resolve forces. So now let's get back to that example that we started from. We had this force acting 40 Newton in this direction, 30 degrees with the horizontal. What we do is we want to find out the resultant force. Now, for finding the resultant force, we do something like this. We say, okay, let's resolve these forces. So for this 40 Newton force, first of all, what are the two components that you get for this? One component to the right side, that's adjacent to the angle, that's going to have cos with it. The other component is on the other side of the angle, that is going to have sine with it. So this component has sine. These are the two components that we've got for the 40 Newton force. If we have this force 60 Newton acting in this direction, what are the two components of this going to be? One acting towards the left side, that's cos 45, because this angle is 45 here, and the other is going to be 60 sine 45. And similarly for the third force down there, that was 30 Newton. This 30 Newton force has two components, one acting towards left, one acting downwards, 30 sine 10 and 30 cos 10 respectively. Now, if you have to find the resultant force, how would you do that? You would represent these forces like this. You've got some forces acting in the horizontal direction. You've got some forces acting in the vertical direction. These are horizontal forces, the yellow ones, and blue ones are vertical forces. Now, to find the resultant, what we do is we first of all find the horizontal resultant and the vertical resultant. So the yellow forces that you see here, what we do is using them, we find the horizontal resultant. So what we generally consider in cases like these, we consider one side positive. For example, we can say right side is positive, left is negative, upwards is positive, downwards is negative. Just like we have it in Cartesian plane, XY axis that you have, right side is positive, left is negative, up is positive, down is negative. So we consider it like this as well. So in this case, resultant in the horizontal direction, what would that turn out to be? You would say 40 cos 30, that's acting towards right, minus the forces acting towards the left side. They are 60 cos 45 and 30 sine 10. So that's going to be your horizontal resultant. That turns out to be minus 13. What does that tell you? Since it's negative, we were considering the right side positive. The resultant of these forces is going to act towards the left side. It's 13 Newton towards the left side. Now, similarly, what we do is we find the vertical resultant. What does the vertical resultant turn out to be? We add these forces, subtract this from that. And the vertical resultant turns out to be something like this. 40 sine 30, that was one force acting upwards. 60 sine 45, we add them up together, subtract from that 30 cos 10, and that simplifies to 32.88 Newton. That's the vertical resultant. And now what we do is, once we've got the horizontal resultant and the vertical resultant, what we've got is that there's a horizontal resultant acting towards left of 13 Newton. There's a vertical resultant, since this is positive, that's acting in the upwards direction, that is 32.88 Newton. How do you find the overall resultant now? You make a right angle triangle like this. Now you say, okay, we've got one horizontal force now that's acting towards the left side. That's this 13 Newton. We've got one vertical force that's acting in the upwards direction. That goes like this. So we make a horizontal force like this, a vertical force like this, and we make a right angle triangle from that, because we know when we have a right angle triangle, finding resultant from a right angle triangle is pretty straightforward. You just make a triangle out of that. The hypotenuse gives us the resultant. So that's what we do here. We've got these two forces, these two resultants, one acting in the horizontal direction, the other acting in the vertical direction. The hypotenuse of this is going to give us the overall resultant. Okay, now how do you find the hypotenuse? Using Pythagoras, you say 13 square plus 32.88 square. That gives us the value for r. Using tan, you can find this angle theta. And how would you describe this angle theta? You would say this is theta degrees, 68.4 degrees above the positive x-axis. That's your resultant. You say the resultant is 35.4 Newton at 68.4 degrees above the negative x-axis. This is the negative x-axis. It's above that. That's your final result. Okay, that's your final resultant. So that's what we do. When we are finding resultant of a set of forces, what we do is we resolve forces. When we have resolved the forces, we find the horizontal resultant, that's Rx. We find the vertical resultant, that's Ry. We square them, we add those two numbers, take square root of that, that gives us the overall resultant. And then using tan, we find the angle of that resultant, and then we can describe that resultant. Okay, now, this is one example of this. You can have a look at this. Fairly straightforward. You've got some forces acting like this. And what you want to do is you want to find the overall resultant. Again, what we do is resolve the forces, find the horizontal resultant. That turns out to be this 5.018. Then we find the vertical resultant. That turns out to be this. Using Pythagoras, we find the overall resultant after making a right angle triangle like this. And then we would describe the direction based on the angle that we've got. Okay, you can have a look at this. This is another example. Now, this is important. Sometimes what they do is, instead of asking you to find the resultant, what they'll do is, they would say, the resultant is given. And there's some force that is missing in the original data. Let's have a look at this example. It says two forces that have magnitudes of P Newton and Q Newton like this. The resultant has magnitude 12 Newton. So they have given you what the resultant force is, and they have shown you that resultant here as well. That's 12 Newton. And then they want you to find the value of Q. We've got the angles of the other forces there as well. They want us to find the value of this Q force. Now, how do you do that? Now, when you are finding the resultant, do not consider 12 Newton as an actual force. That's the resultant of the actual forces that we're applying. The actual forces, this P Newton and this Q Newton. These are the forces that are acting. 12 Newton is not a force. It's the resultant of these two forces. Now, how do you find the value for Q in this case? You say the resultant is 12 Newton, right? The resultant is 12 Newton. That's what they've given us. And the angle at which it's acting is 80 degrees. What we can do is we can find the horizontal and vertical components of this resultant. So this will be Rx and this will be Ry. So Rx is 12 cos 80 and Ry is 12 sin 80. And then what we do is we say, okay, these are the values of Rx and Ry. Using these original forces, which were P and Q, we find our own resultant. So for example, what is Rx going to be? After we've resolved the force P, horizontal resultant would be Q minus P cos 60. That's the horizontal resultant. But they told us that the horizontal resultant is supposed to be 12 cos 80. So we equate it with that and we get an equation like this. Similarly, the vertical resultant. In the vertical direction, we only have one force that's acting, and that's in the upwards direction in this case, and that is P sin 60. That's the vertical resultant that we've got. The value for that is P sin 60. They gave us that this is actually supposed to be 12 sin 80. So we equated with that. We get two equations like this. We solve them simultaneously, find the value of P and Q from that. Sometimes this can happen as well, that they give you the value for resultant, and you have to find some missing force in the actual data. So you compare both of them. You find the horizontal and vertical resultant from the given resultant. You find your own values of Rx and Ry, and then you equate both of them to find any missing force that is there. Now, the next is the concept of equilibrium. Now, before we do that, just a quick question that somebody asked here, so I'll just respond to that. So it was about reaction. So there is going to be reaction in this case as well, yes. So we would have reaction in this example that's acting in this direction, but that was not the point. We were considering how to resolve forces. So this is how we resolve the 60 Newton force, this is how we resolve the weight. But yes, reaction is going to be there in this case, but that's already perpendicular to the surface. So we don't have to resolve it in this case, because we only resolve forces in these two directions. Resultant is the normal reaction is already in this direction, so we don't resolve that. So that's why I did not show that there. But yes, that will be there, of course. Okay, now the next is the concept of equilibrium. So we talked about how to find the resultant of a set of forces. Now, what is equilibrium? Equilibrium is when you have a set of forces that when they act on an object, the overall impact, the overall resultant is equal to 0. Or in other words, we can say, in this case, for instance, the resultant is 0, but it also follows from that, if the resultant is 0, the forces acting towards the right side, they should equal forces acting towards left. 7 plus 5 should equal 12 in this case. It does equal 12. That's why it's in equilibrium. Similarly, in the vertical direction, 6 plus 3, that equals 9. So in the vertical direction as well, we've got forces that are equal to each other. So whenever you have equilibrium, whenever they say something is in equilibrium, what we do is we just equate opposite forces. So if it's a horizontal, if the forces are horizontal and vertical like this, we say the forces acting towards the left side, they should equal forces acting towards the right. And the forces acting in the upwards direction, they should equal the forces acting in the downward direction. Now, that's not always true. It is only when you have equilibrium. Don't put them equal to each other in every single case. This is only true when you have equilibrium. Otherwise, they are not necessarily going to be equal to each other. So left equals right, up equals down. That is what you do when you have equilibrium. When you have an inclined surface like this, what about that? On an inclined surface, we consider directions like this. Think of yourself as standing on this plane, on this surface. So standing on the surface, what would be the upward direction for you? This will be the upward direction. This will be the downward direction. This will be your left direction if you're facing the screen, and this will be the right direction. So in an inclined surface, the understanding of left, right, up, down changes like this. Okay. Now, a point to note here: whenever you have an inclined surface and the object is moving, for instance, these forces are always going to be equal to each other. Perpendicular forces to a surface, they will always be equal to each other in your syllabus, because in your syllabus, objects can only move in a straight line. There can't be any projectile motion like this. So that means the perpendicular forces, these forces, they will always be equal to each other without exception in your syllabus. If the object is moving, that will only be along the surface like this. So right or left, if the object is moving, one of them will be bigger and the other would be smaller. But these forces are still going to be equal to each other, no matter whether the object is moving or not. Okay, now this is one thing that confuses some people. So they say there's a particle P that is in equilibrium on a smooth horizontal table. So we have a horizontal table under the action of horizontal forces. We've got these forces that are represented there. We need to find the values of F and G. Now, since it's equilibrium, what we can do is we can just find the components of each force, equate the opposite forces, left equals right, up equals down. That's what I've done here. Resolve the forces, equated the opposite forces, left equals right and up equals down. However, they've also given, they've not given, but you could also think of, sometimes what happens is, in this case, it's not given, but sometimes what happens is in the next part, you need the mass as well. For some reason, you might have to use Newton's second law of motion, and they might give you the mass of this particle. Let's say that's 5 kilograms. Now, do not represent the weight of the object on this diagram. You do not say that there's a weight of 50 Newton acting in this downward direction as well. That is not going to be there. It's a horizontal table and the forces are all horizontal. So you think of it like this, that it's a table like this, the yellow table, it's horizontal. The forces that you have, let's say, this is from another example, this is a 2.5 Newton force, this is an F Newton force, this is a 2.6 Newton force. They are all acting within the table, right? Along the surface of the table. Weight acts perpendicular. Weight acts vertically downwards. So the table is horizontal. Weight will be acting vertically downwards. Now, weight does not have anything to do with the rest of the forces in the table. That's a perpendicular direction. Weight does not have any component acting in this direction. So when you have horizontal forces acting on a horizontal table, on a horizontal surface, weight is not going to be considered as one of the forces. You are not going to represent weight here in this case. Okay, so even if they gave you mass, that would be used for some other part. Maybe they want you to find acceleration in the next part, but do not add that as a force here. That is not going to be relevant here. Okay, now we've got some forces that you need to know about. So in a lot of cases, they will tell you some forces in the question itself, but there will be other forces that you'll have to represent yourself that they will not tell you about in the question statement necessarily. So what are those forces? There are 4 forces like that you always need to think about in any situation, that whether they are applying or not. The other forces, they will always tell you. So what are those forces that you have to think about yourself? We've got weight, normal reaction, tension, and friction. These are 4 forces that you'll have to think about yourself, that whether they're acting in a particular situation or they're not acting. Okay, weight, normal reaction, tension, friction. Now let's start with weight first of all. What's weight? Weight is just the force that Earth is applying on an object. Its definition is mass into gravity. In mechanics, what we do is we take the value of gravity as 10 meters per second square. You should use that value. Do not use 9.81. They instruct at the start of the exam that you should be using 10 here. 9.81 is going to complicate a lot of calculations for you as well. So make sure that you use 10 here. Weight is defined as mass into gravity. For example, if something has a mass of 15 kilograms, its weight is going to be 150 Newton. Just multiply that by 10. Now, weight is also a force. So its unit is going to be Newton. The direction of weight is always vertically downwards. It always acts vertically downwards. That's important. So if you have a horizontal surface like this, for instance, where is the weight going to act? Weight is going to act vertically downwards in this direction. If you have an inclined surface, that does not change anything. Weight is not because of the surface, it's because of the Earth. It still acts vertically downwards. The direction of weight is going to be this. It acts vertically downwards like this. All right. But then since it's an inclined surface now, you would have to resolve it in these 2 directions along the surface and perpendicular to the surface. How do you do that? If the angle of the plane is theta here, we talked about earlier that this angle here is also going to be theta. So the components are going to be W sine theta and W cos theta along the surface, W sine theta and this W cos theta when you resolve this weight. Then you've got normal reaction. What's a normal reaction? Normal reaction is the force that a surface applies on an object. It's the force applied by a surface on an object. Now, for example, let's say you've got this horizontal surface. In this case, you've got a weight acting in the downward direction. That's 150 Newton. Now, because of this 150 Newton, the object is not going into the surface. It's staying in its position. Why is it staying in its current position? Because there's an equal and opposite force acting in the upwards direction, and that's normal reaction. That's 150 Newton in this case. In the absence of any other forces, this will be 150 Newton as well. This is reaction. Now, normal reaction always acts perpendicular to the surface. It always acts perpendicular to the surface. So whatever the surface is, the direction of normal reaction is going to be perpendicular to that. It's not always going to be equal to or opposite to weight. Now, in this example, you can see that it's equal to weight and it's also opposite to weight, but it's not always going to be true. For example, if you have a situation like this, still have a horizontal surface and the weight is 30 Newton. However, there's also an upward force that you're applying and that's 10 Newton. Then the reaction is not going to be 30 Newton. It's going to be 20 Newton. That's going to be the balancing force. So if you have 30 Newton acting downwards, upwards as well, you should have 30 Newton if the block is not moving. Then R plus 10, that means reaction plus this force. This should equal 30. So the value of R that you end up getting from that is 20 Newton. If the block is in equilibrium, that's the value of R that you get. So it's not equal to weight every single time. And on an inclined surface, for example, if you have weight acting in this direction, 90 Newton vertically downwards, where does reaction act? Reaction does not act opposite to weight in this direction. It acts perpendicular to the surface. Now the surface is inclined like this. The direction of reaction is going to be this. Okay. And what is that going to be equal to in this case? This component of weight, 90 cos 40, reaction is actually going to be equal to this component. It's not going to be equal to 90. It's going to be equal to 90 cos 40 in this case. So in this case, you can see it's not equal to weight and it's also not opposite to weight. It's always going to act perpendicular to whatever the surface is. Now, sometimes you'll see situations like this as well. You'll have something vertical. For example, you have a rod like this, and on this rod, you have a ring that is tied like this. So this is a ring that's tied to the ring. Now, in this case, let's say we've got some forces acting. We've got the weight acting in the downward direction, of course. Let's say that's 0.5 Newton. There's a force acting in this direction, that's F Newton. What are going to be the components of F? One in this direction, the other in this direction, F sine 25 and F cos 25. You can see them on the diagram. If this angle is 25, this is cos 25, this is sine 25. Now, if the object is in equilibrium, if the ring is in equilibrium, what does that mean? Opposite forces have to be equal to each other. Now, this force is actually applying, this force is actually acting towards the right side. It's trying to make the ring move towards the right side, but the ring is not moving. It's tied to the rod. It's not moving to the right side. Why is it not moving? Because the rod is going to apply a force and towards the left side, and that's going to be the normal reaction in this case. A rod is the surface. This normal reaction is perpendicular to that rod. It acts towards the left side. Why? Because this force was acting towards the right. Reaction is going to balance that force to keep this ring in equilibrium. Now, if there was a force acting towards the left side, for example, that was a bigger force. Let's say that was a 70 Newton force. And if we knew that F was less than 70, then reaction could act towards right as well. So reaction can act either towards right or left in this direction. It could be this, it could be this. It would depend on the rest of the forces. If you have more forces acting towards right, reaction will be to the left to balance those forces. If you have more forces acting towards left, reaction will be towards right, again to balance those forces. But it has to be perpendicular to the surface. Like in this case, it's going to act towards the left side like this. So that can also happen. All right. Okay, now let's have a look at this example. It's pretty straightforward. You've got some forces acting here. You're given that it's at rest. At rest means that it's in equilibrium. Opposite forces are supposed to be equal to each other. And in the first figure here, you can see you've got some forces acting like this. You've got P Newton acting in this direction. That's the only force that they give you. Now you have to think about the rest of the forces yourself. The weight is 12 Newton. Where does that act? That acts vertically downwards. Since you have a surface involved, whenever you have a surface in contact with an object, you would always have normal reaction. And that is going to be perpendicular to the surface. The direction of normal reaction is this. Now, if we want to find the value for P, what we can do is we can just equate the opposite forces in this case. In the first case, P is equal to 12 sine 40, and that gives the value for P. You can see what that is. Okay. In the second example, if the force is acting like this, it's P Newton. What about the value for P? In this case, again, we resolve the forces, equate the opposite forces, and that's going to give us the value for P. Now, this is very important. Whenever you have a force acting like this, a lot of people end up resolving it wrong if it's represented like this. If it's represented like this, in which direction is the force acting? The force P, it's acting towards the right side, right? The force P is acting towards the right side. I would recommend that you represent that force on the side that it is acting. Now, it's pushing the object to the right side. So the direction of force is towards the right side. It's going to make you do less careless errors while resolving this force if you represent it on that side. Okay. Now, if you represent it on that side, we can clearly see this angle is 40. This angle here is also going to be 40. These are corresponding angles. And then you can resolve it like this. This angle, this component is P cos 40 in this direction. The other component in this direction, that's going to be P sin 40. Equate the opposite forces, and that's going to give you the value of the unknown that you have there. And you can find that like this. Okay. This is an example that we've already talked about before. So for example, in this case, you see the first part, you are given that this is in equilibrium. This object is in equilibrium, and they've given you mass because that is actually required for the next part of this problem. In the first part, a lot of people end up doing this mistake. They say that there's going to be a weight. There's going to be weight acting in this direction as well. That's 5 Newton, but that's not true. That's not going to be true because the forces are horizontal. These are horizontal forces. It's a horizontal plane. So weight is not going to be considered as one of the forces in this case because the forces that we've got here, they are all acting inside that horizontal plane. Weight acts perpendicular to that. That does not contribute to the forces acting along the surface. So we do not consider weight here. Okay, so we already talked about this before. Let's move on to the next force. That's it. That is tension. Yes, that's correct. That's correct. So reaction will be acting towards the side that has less forces. Yes. Now, what about tension? Tension is a force that a string applies on an object. It's a force that a string applies on an object. Let's consider this example. You've got this rod, and this rod has this string tied to it at this particular point. So this is the point at which the string is tied. Now, the block is hanging from this string in the vertical direction like this. The weight of the block is 50 Newton, mass is 5 kilograms. Now, since there's weight of the object, that's pulling this block in the downward direction, but it stays in its current position. Why does it stay in its current position? Because the string is applying a force on this block as well that is keeping this block in its position. What is that force? We call that force tension. And the tension in this case is going to be 50 Newton. Why? Because if it's an equilibrium, if weight is 50, to balance that, tension is also going to be 50. Now, tension is the force applied by a string on an object. It's the force applied by a string on an object. What about the direction of tension? Tension always acts away from the point of reference. Away from the point of reference. Tension always acts away from the point of reference. Now, what exactly does that mean? Okay, so this is going on. We'll have a 1 minute break, and then we resume after that. I'll continue from here. We will have a break from Maghrib after forces in equilibrium. Inshallah, hopefully we'll get done with it in about 20 minutes, and then we will talk about the next forces. Yearly 𝗣𝗀𝗀𝗃𝗲𝗿. No, that's not public. You'll not be able to access that. I'll share the recording later on. Okay, let's resume. So what about tension? Tension, as I said, is the force applied. Tension is the force applied by a string on an object. Now, tension always acts away from the point of reference. It always acts away from the point of reference. Now, what does that mean? If you consider tension from the perspective of the block, on the block, this string is applying tension in this direction, away from the block and towards the string in the upwards direction. But at the same time, the string is also tied to this point on the rod. So if you consider from the perspective of the rod at this particular point, on the rod, the tension acts in the downward direction. On the rod, the tension acts in the downward direction, away from the rod and towards the string. So whatever is the point that you that's your point of reference, from that tension is going to act away in this direction and towards the string. Yes, if it's a single string and on both sides you've got one point here and you've got another point here, the tensions on both sides of that, they're going to be equal to each other. Yes, because it's a single string is in its in equilibrium position as well. It's not moving. If it's not moving on the string, you have equal forces acting in both directions. That is why it is in its current position. So if this tension is 50 Newton, this is also going to be 50 Newton. They're both going to be the same. Now, why is it that the tension is always going to act away from the point? Because think about a string. If you have something placed like this, and you have a string tied to it, tied to that block, tied to this block. Now, with a string, you can only pull the object towards yourself. You cannot push something with a string, right? If it was a rigid object, as we'll see later, sometimes what you have is a rod like this, and that is tied to an object. With a rod, you can both push and pull. But with a string, you can only pull something towards yourself. So that is why with a string, the tension always acts away from that object and towards the string in this direction. Now, a lot of times what will happen will be you will have multiple strings. You'll have multiple strings. Okay. Yes, of course, direction will be different. Magnitude will be the same. Direction will be different. Yes. If you've got multiple strings like this, let's consider this scenario. You've got this ring that is hanging from a string like this, that one part of the string is tied to the point A here, and the other part of the string that is tied to the point B here. And the string is passing through this ring, and the ring is hanging like this. Now, when you have anything like this, a single string and the object that is attached to the string, the string is easily able to pass through that. It's easily able to slide through that. In that case, the tension on both sides is going to be equal. Compare that with something like this. In this case, we've got two different strings. One that is string 1 on the left side, the other string 2 on the other side. But in this case, what's happening is the strings are tied to this object. There's a knot on this object. So in this case, the string is not free to move through the object. When you have a situation like this, the tensions on both sides are not going to be considered equal. If you call one of them T1, the other will be called T2. In the first situation, we called both of them T. Now, what exactly is the difference between them? Tensions are going to be equal when both of these conditions are met. It should be a single string. And it should be free to slide or move through the object. For example, if you have a ring like this, string can easily slide through that ring. So in this case, tensions on both sides are going to be equal to each other. This is one common case that you'll see, the case of a ring. The other common case that you'll see here would be of a pulley. If a string is passing over a pulley like this, in this case as well, tensions on both sides of the pulley for that same string, they're going to be equal to each other. So if you call one of them T, the other is also going to be T. Okay. In the other case, the tensions are not going to be equal. What's the other case? It could either be a single string that is not free to slide because of this knot, or it should be two different strings. Whenever you have two different strings, in that case as well, we do not assume that the tensions are equal. They may sometimes end up being equal, but we are not going to assume that. So the common cases that you will have in your syllabus when the tensions are going to be considered equal, they are going to be either when you have a ring like this, or when the string is passing over a pulley. The general rule is when it's a single string that is free to slide or move through the object. Because think about it, if you have a ring in this position, if you were to apply a force towards the right side, because of that force, what would happen would be, let's say that you've got this force F that's acting towards right side. Since the string is free to slide through the object, the length of the string on the left side and the length of the string on the right side, this is going to adjust in such a way that the ring comes in equilibrium position again like this. And the tension on both sides, they're also going to adjust and they will become equal to each other. Compare that with the other case. If there was a force acting towards right side in this case, since there's a knot here, the string, they cannot change their length as because the string is not free to slide through the object. Because of this force that's acting towards the right side, there's going to be more pressure on T1, right? When you pull this object towards right, there's going to be more pressure on this point. So T1 is going to be bigger than T2 in this case, right? So that's the idea behind it. But that's what you need to remember now. Single string free to slide, equal tension. But that condition is not met. Any of these conditions, whether it's a single string, if that condition is not met, or if it's not free to slide, you say the tensions are not going to be assumed to be equal to each other. All right. The common cases are ring and pulley, as we discussed. Let's take this example. Let's say we've got an object like this. It's a ring, and this ring has a string passing through it. One end of the string is tied to the point A here. The other end is tied to the point B here. Now, at the ring, we've got some forces acting. What are those forces? We've got X Newton acting towards right side. We've got weight acting in the downward direction. And there are going to be tensions, one in this direction and the other in this direction. These are two tensions that we've got. They are both going to be equal to each other. Why? Because it's a ring. The string is free to slide through the ring. The tensions are going to be considered equal to each other. Now, the question statement is also going to hint about it in some way, because in this case, you see the question says find the tension in the string. They're not using a plural here. Find the tension. That means it has to be equal. It can't be multiple tensions. If they specify, find the tension in the lower string, find the tension in the upper string, find the tension in one of the strings, or find both tensions. In that case, you know that the tensions are going to be different. Okay. Yes, it's free to slide because it's a ring. Through the ring, the object can move. It'll always be smooth if it's a ring. It'll always be smooth. You don't consider friction in case of ring generally, at least not until now in past papers. There's always the first time. But in that case as well, the tensions are going to be equal. There's just going to be some friction added there. But I think that will become too complicated. Let's not get into that. You'll always have a smooth ring. And in that case, yes, it's going to be equal. But the main reason for that is, in the second case, there's a knot. So the string is not free to slide, as in it can't, the length on both sides, that cannot change. That will remain the same in the second example. And that's what is causing the tensions to be different. Because of this extra force that might act, there's going to be more pressure on one of those tensions and there's going to be less pressure on the other one. Okay, all right, let's move on. So in this case, the tensions are going to be equal to each other. All you have to do now is, since it's equilibrium, resolve the forces, equate the opposite forces. Forces acting towards left equal to forces acting towards right. Forces acting upwards, they should equal forces acting in the downward direction. This is another example. We've got this, what's this? It's this particle. We've got this particle, and the particle is attached to two strings. One is S1 and the other is S2. Now, these are two different strings. When you have different strings, tensions are not going to be equal to each other. So we're not going to assume them to be different from each other. Again, in this case as well, what do? Since it's equilibrium, we resolve the forces, equate the opposite forces, and that will give us the result. And what's the new thing here? Sometimes what happens is they give you the lengths of the strings like this. One string is 0.52 meters, the other is 0.2 meter, the other is 0.25 meter, and this height is 0.2 meters. Whenever they have these lengths given for the string or some distance like this, that the only reason why that is given is going to be to find the angles. You can use those lengths along with a right angle triangle to find those specific angles. Once you've got the angles, there's no other use of these lengths. Okay, so these lengths are only going to be used to find angles. Once you find those angles, just get rid of them because they're not forces. That we are not going to consider them anymore. And then we just equate the opposite forces. First resolve the forces, equate the opposite force, and that's going to give us the result. Okay, all right. Let's move on. We can sometimes have something a bit more complicated like this as well. What I'll do is I'll just zoom in a little, and that might help. So we've got this point X in the middle, this point X in the middle, this point here. And there are three strings that are attached to this point. There are three strings that are attached to this point like this. One is going here, the other is going, another is going here, and another is hanging below like this. There are three strings. Now consider the one on the left side. This string is passing over a pulley. Now on both sides of the pulley, the tensions are going to be equal to each other. So whatever is the tension on the left side here, that's going to be the same as this tension on this side here. Now we know at the point A, this is an equilibrium situation. So point A is also an equilibrium. The particle is in equilibrium. That means downwards we've got 5.5 Newton. Upwards we've got tension. So tension is also going to be 5.5 Newton. If this is 5.5 Newton, that also implies that this tension here on the other side, that's also going to be 5.5. Right? So on both sides of a pulley, the tensions are going to be equal to each other. Similarly, on the other side of this diagram here, you can see we've got weight acting downwards, that's W Newton. So the tension is also going to be equal to W because the object is in equilibrium. Now, if this is W, that implies that this tension here, that is also going to be W. Okay. And now you've got a situation like this. You've got this point X. There's one force acting in this direction. There's another force acting in this direction. There's another force acting in the downward direction. That's 7.3 Newton. Weight is 7.3. So the tension on the particle B is going to be this. If that's this, then the tension on X in the downward direction is also going to be 7.3. So we've got three forces acting at the point X. 5.5 in this direction, W in this direction, 7.3 in this direction. You can resolve the forces, equate the opposite forces, and that will give you the result. So in this case, you can see if we've resolved the forces, equated the opposite forces, left equals right, up equals down, and that gives you the result. You can go through the working. That's how it would work. Okay. All right. Then now this is something that's not explicitly part of the syllabus, but sometimes they give this as an alternative solution in some questions, and it makes some specific questions very straightforward and very quick. And what's this? This is something that we call Lami's theorem. And this can be used when two conditions are met. Number one, object is in equilibrium. And number two, you have exactly three forces. When both of these conditions are met, you've got equilibrium, and you have exactly three forces. In equilibrium, when you have exactly three forces, they have to be coplanar, of course. You can't have forces acting in different planes. They have to be coplanar, of course, but exactly three forces. You can't have 4, 5, exactly three. When you have three forces, then this holds true. F1 over sine of this angle, the angle opposite to that, that equals this F2 over sine of the angle opposite of that. And that equals F3 of the sine of the angle opposite of that. Now, as you might have guessed, this comes from sine rule. If you make a triangle out of that, you get the sine rule. It comes from that, but that's what Lami's theorem says. And that makes some problems very quick, some 5-mark questions. The normal way would be to resolve the forces. You find the horizontal component, vertical component for this, find the horizontal, vertical components for this. And similarly for all the forces, all the three forces, then you equate them, solve simultaneous equations. Using Lami's theorem, you can do some of those questions in like 2-3 steps. And that makes it a lot quicker, a lot more efficient. Let me see if I can find one example of that for you quickly, where I've used Lami's theorem somewhere. Just give me a second. This is forces and equilibrium. Lami's theorem. No. Okay, so a similar example to what we saw previously. You can see the solution. We've got the angles given. We've got this point P. We've got this point P. At this point P, we've got a force acting in the downward direction. There's another force acting towards right. That's T2. Another force acting here. That's T1. Three forces, and the object is in equilibrium. The object is in equilibrium. Three forces. What we can say is, we can use sign rule. It's a 5-mark question. You can do this in 2 steps like this. What do? You say this force T1 that's acting in this direction, what's the angle opposite to that? You've got these lengths, so you can find those angles using that. Okay, so the angle opposite this turns out to be 112.62. You can see the calculations for that above here. This angle is 104.25. This angle is 143.13. So make an equation like this. T1 over sine of 112.62, that equals 21 over sine of this angle. And that also equals T2 over sine of this angle. And you get 2 equations from that. You can make an equation from these 2. You can make an equation from these 2. Find the values of T1 and T2 from that directly. You won't have to resolve the forces. You just do it directly like this in this case. Okay, have a look at this. If you don't know this and you think it's complicated, just leave it. It's not required. But those of you who know it, you might know that this is pretty helpful. But the condition has to be met. The condition is 3 forces and equilibrium. That's the only case you use it. That's a very common case in past papers, so that's why it helps sometimes. But remember, no other case you can use Lami's theorem. This is the only case: equilibrium and 3 forces. Okay, let's move on. Okay, let's resume that. So the next force that we've got is friction. Now, we talked about normal reaction before. Normal reaction is when an object is in contact with a surface and the surface applies a force in the perpendicular direction to the surface. There's another force that we also have when 2 objects are in contact with each other, when the surface is rough, and that is friction. Now, normal reaction always used to act perpendicular to the surface. Friction always acts parallel to the surface. Friction always acts parallel to the surface. And both of these together, they're called contact forces, right? This terminology is important. Sometimes they use this in questions. Contact force is the force that is due to contact between 2 objects. When 2 objects are in contact with each other, the forces that we have because of that contact are called contact forces. There are 2 of them. One is normal reaction, that's perpendicular. Friction, that is parallel to the surface. Now, let's consider this example. Let's say you have an object like this. It has a weight of 500 Newton. If you were to apply a very small force in one direction, for example, just 0.1 Newton towards the right side. Now, because of the small force, practically speaking, it's very unlikely that the object will start moving to the right because it's so heavy, 500 Newton. You're just applying a very small force in this. Practically, what happens is the surfaces that you have, they have some roughness in them. So if it was a perfectly smooth surface, theoretically, then even a small force will make it move. But generally, that does not happen because you have some rough objects. So if you apply this force 0.1 Newton, why does it not move? Because the surface applies an equal force towards the left side that keeps the object in its current position and does not let it move. Okay, that's called friction. It's the force applied by a surface on an object that opposes the motion of the object. It opposes the motion of the object. It does not let that object move. So it always acts parallel to the surface and opposite to the possible direction of motion. Why possible? Because in this case, the object is not actually moving, but in which direction can it possibly move? It can possibly move towards the right side because of this force. Friction stops it from moving, so it's acting opposite to the possible direction of motion. So it acts in this direction. Now, what do we need to know about friction? It has some maximum value. So for example, in this case, if you have an object, 50 kilograms, 500 Newton weight, if you apply a force of 90 Newton to the right side, let's say the object does not move because of that. But if you were to apply a force of maybe 9,000 Newton on the right side, what about that case? If you apply such a large force, it's very likely that the object will start moving, even if there is friction between them, because we're applying such a large force. Now, between So let's actually compare 9,000 and maybe just 0.9 Newton. So if you're applying 0.9 Newton, it's very unlikely that the object will move. 9,000 Newton, that's extremely large. It's very likely that the object will move to the right. What's that cutoff point at which the object starts moving? That is going to be somewhere between 0.9 and 9,000, right? That cutoff point is what we call the maximum value of friction. So friction always, in any context, will have some maximum value after which it would not be able to stop the object from moving. Let's assume for now, in this case, that the maximum possible value of friction was 100 Newton. We'll see where this comes from. But let's say this was 100 Newton. Now, if this was 100 Newton, what happens is, if we apply a force of 90 Newton to the right side, the object does not move because friction is able to counter that. If we apply a force of 100 Newton to the right side, again, it does not move because friction can equal 100 Newton as well, and it stops the object from moving. However, if you increase the force even slightly more than that, let's say apply a force of 101 Newton to the right side, maximum possible value of friction was 100. So the object, the friction cannot stop the object from moving anymore. Friction stops at 100 Newton. It cannot increase to more than 100. So what happens because of that is the object has a resultant force of 1 Newton that makes it start moving to the right side. So friction has a maximum value. Friction has a maximum value. If you apply a force that is greater than the maximum value of friction, the object will start moving. Now, where does that maximum value come from? There are two things that basically decide what the maximum value of friction is going to be in a particular context. Number one is something that we call the coefficient of friction. This basically quantifies the roughness of the surfaces. So if the more rough the surfaces, the higher its coefficient of friction is going to be. It's represented by mu. So if a surface has more roughness, it has more friction. And the second thing that friction depends on is normal reaction, because normal reaction basically captures how strongly two objects are connected to each other. So if the strength between two objects is between an object and a surface is more, strength of contact between two objects, if that's more, then the friction is going to be more. For example, take this case. In the first example, you've got a weight of 200 Newton. There's a normal reaction of 200 Newton as well. These are connected to each other by a force of 200 Newton, the object and the surface. In this next example, we've got the weight acting downwards, that is 200 Newton, but we are also applying a force acting in the upwards direction, that's 50 Newton. Now, the net force that is actually applying on the ground, and the ground is applying on the object, that is only 150 Newton. So in this case, the strength of contact between the two objects, that is reduced, and that strength of contact is actually captured by this normal reaction. So that's the other thing that maximum value of friction depends on. Now, that's the logic behind it, but now you just need to remember, maximum value of friction is given by mu times r. Okay, that's the formula that you need to remember. F max equals mu times r, where mu is the coefficient of friction and r is the normal reaction. These are two things that the maximum value of friction depends on. Now, let's go back to that same example that we saw before. In that case, if we knew that the coefficient of friction was 0.2, in this case, you can say, you can see that the weight was 500, so normal reaction in this case would also be 500. So mu times r, that gives you 100 Newton. So that's the maximum value of the friction. And then we looked at these cases. If we were applying a force of 90 Newton, the object will not move. 100 Newton, the object will still not move. 100 Newton, the object will start moving. So when the force that you're applying becomes greater than the maximum value of friction, what happens is the object starts moving. When the force that you're applying is equal to the maximum value of friction, we call this equilibrium, but it's a specific case of equilibrium, and it's called limiting equilibrium. It's called limiting equilibrium. Why? Because the equilibrium has reached its limit. Even if you were to increase this force even by a very small amount, what would happen would be the object will start moving. So equilibrium has reached its limit when the force that you're applying is equal to the maximum value of friction. So in both of these cases, you see, friction is at its maximum value. When the object is moving, F is equal to mu r, the friction will stop at that point. And also when you have limiting equilibrium, friction is at its maximum value in both of these cases. If the force that you're applying is less than, it's a force that you're applying, so it's any force that you're applying, right? So we're applying a force to the right side. We're calling that P. We could call that anything. If we're applying a force of 90 Newton, that is less than the maximum value of friction. In that case, we call this non-limiting equilibrium. That it's equilibrium. The object is not moving because friction is also 90. This is also 90. The object is not moving, but it's not at its limit yet. If we were to increase this force by 1, for example, 91 Newton, friction will also become 91 Newton. If we increase it to 92 Newton, friction will also increase to 92 Newton. So it's not limiting equilibrium. We call this non-limiting equilibrium. So we got these three cases that you need to remember from this. Whenever an object is in motion, or its limiting equilibrium, we have F equal to mu r. We have F equal to mu r. Okay, this is the limit, maximum value of friction, mu times r. In both of these cases, when the object is in motion and when it's limiting equilibrium, F is equal to mu r. When it's non-limiting equilibrium, friction, that means it's not at its maximum value. It will be less than that. You can see that here. The value of friction is less than the maximum value. F is less than mu r. If you were to combine these two cases, in equilibrium, friction can either be equal to the maximum value or it can be less than the maximum value. When it's limiting, it's equal to mu r. When it's non-limiting, it's less than mu r. If we combine these two cases, we can say whenever we have equilibrium, that means friction is either less than or equal to mu r. Now, this case is not used a lot in past papers when you have non-limiting equilibrium, but you'll see this used a lot whenever the object is in motion or limiting equilibrium. In both of these cases, remember, you will say F is equal to mu r in both of these cases. And sometimes they will say that the object is in equilibrium. And they will ask you to prove some inequality or find some inequality. In terms of mu, the coefficient of friction, they'll ask you to find some inequality. In that case, remember, whenever an object is in equilibrium and you want to form some kind of an inequality, in equilibrium, the general rule is F is less than or equal to mu r. F is less than or equal to mu r. We'll have a look at some examples of this. So this is what you need to remember. F is equal to mu r when it's in motion or it's limiting equilibrium. F is less than or equal to mu r when it just says that it's equilibrium and it does not specify whether that equilibrium is limiting or non-limiting. Now, for limiting equilibrium, sometimes they will say in the question that the equilibrium is limiting or it's limiting equilibrium. Sometimes they say that same thing in some other words. You need to be familiar with these phrases. When an object is just about to move, just about to slide, just about to slip, that means the equilibrium is at its limit. It's on the point of moving, on the point of sliding, on the point of slipping. Again, that is another way of saying that this is limiting equilibrium, that the object is just about to move. And in this case, what you would do would be, you would say F equals mu times r. Let's take an example. Let's say we've got the surface. Let's just look at the second part of this. First part is fairly straightforward. And the first part, surface is smooth. So you would just resolve the forces since it's equilibrium and equate the opposite forces. Now, in the second part, it says the surface is rough. So we have a rough surface. And the block is on the point of slipping. What do we understand from that? It's limiting equilibrium. It's on the point of slipping. That's limiting equilibrium. So F is equal to mu times r. So what you do in this case is, it's on the point of slipping in what direction? Do we know that in what direction it's on the point of slipping? Let me just read the question statement quickly. We've got tension acting in this direction, 75 Newton acting in that direction. Okay, so they have actually told you in which direction friction acts. I was just thinking about that, in which direction friction is going to act. They have told you explicitly that it's going to act towards A, because otherwise you could not figure that out, because it would depend on whether 75 cos 30 is bigger or T cos 60 is bigger. So in this case, since that's not specified, they have told you the direction of friction. So it's acting towards the left side. All you have to do is just represent all the forces, equate the opposite forces. T cos 60 plus F in the second part. They should equal 75 cos 30. That's one equation. T cos 60 plus F equals 75 cos 30. And in the vertical direction, you have these three forces. In the downward direction, you have 200. So you say sum of those three forces, that should equal 200. You get two equations. Now, since it's limiting equilibrium, you would replace F with mu times R in this case, although in this case, we have to find what coefficient friction. Okay, so you could replace F equals mu R. In this case, what I've done is I've just input the value of F here. That gives me the value for tension and the value for reaction. And once I have that, since it's limiting equilibrium, F equals mu R, and we can say 25 equals mu into 93.301, and that gives us the value for mu. Another way of doing this could be that in place of friction here, we could just write mu times R, or that will be the same thing. It doesn't make much difference. So that's the idea. When you have limiting equilibrium, F is equal to mu R. That's what you have to do. Okay, equilibrium still means opposite forces are equal to each other. Left equals right, up equals down. But whenever you have friction there, in limiting equilibrium case, you would say F is equal to mu R. Now, sometimes what they do is they ask you something like this. Let's have a look at this question quickly. So we have a rough plane. Cos alpha is this, sin alpha is this. Given that the normal component of the contact force, what does that mean? That's the normal reaction. Is 1.2, find the mass of the particle. In the first part, you just know that the normal component is 1.2. Then this R is 1.2. W cos alpha is the weight component. They should be equal to each other. And that gives us the value for W. We can find mass from that. Now, the first part is pretty straightforward. Second part says friction has this value. You equate these forces along the surface, and that would give you the value for, in fact, the particle is moving. You have to find deceleration. Okay, just skip that. That's Newton's second law of motion. What I want to talk about in particular is the last part here. It says the particle is moving. It's going in the upwards direction. Okay, it's moving up. Now, when it moves up, what happens is it comes to rest at some point. It comes to rest at the point X. Let's say this is point X. It comes to rest at that point. Now, at that point, we need to determine whether the particle is going to remain at X or it is going to start moving down the plane. How do you figure that out? So the particle is at the point X. And now, is it going to start moving down the plane, or is it going to stay in its current position? That's what we need to figure out. We think about all the forces that are acting on the point X. We've got weight acting downwards. We've got normal reaction acting here. We've got the component of weight that's acting in this direction. That's W sine alpha. And we've got friction. Now, since the object is going to try and move in the downward direction now when it comes to rest first, now it's going to try and move downwards, friction, that's going to act in the upwards direction, in this direction. Now, that's the direction of friction that we've got. How do you figure out if the particle is going to move downwards or stay at rest there? We can figure out the value for W sine alpha and see what that turns out to be. The value of W sine alpha in this case, we know the value of W, we know the value of sine alpha. That turns out to be 0.35. What about F max, the maximum value of friction? We knew that the friction was 0.4 Newton when the particle was moving. When the particle was moving, the friction was 0.4, and we know when a particle is moving, friction is at its maximum value. So the maximum value of friction is 0.4. So the weight component in this direction is 0.35 Newton. The maximum possible value of friction that we've got is 0.4 Newton. That means this force, 0.35 Newton, is not going to be able to counter friction, and the object is not going to move in the downward direction. It will stay at rest. If W sine alpha, this value was greater, if it was greater than friction, in that case, the object will start moving in the downward direction. Okay. The two components of contact force, they are normal reaction and friction. This is the other component. Friction component, that's the other component. Friction is the other component. Okay. Okay, so F here, in this representation that I have here, F represents friction. F is representing friction. F is not this force. This force is represented by P here. That force is greater than maximum value, yes. With small f, I'm representing friction here. Friction cannot be greater than mu r. Mu r is the maximum possible value of friction. How can friction be greater than its maximum value? That's not possible. Friction has to be equal to the maximum value when the object is either moving or is in limiting equilibrium. Okay, it has to be equal to maximum value. Okay, so this is one thing that you will see as well. You have to figure out whether the particle is going to move or it's going to stay at rest to figure out what the force acting is and what is the maximum possible value of friction. If the force acting in the forward direction is less than friction, the object cannot move. And if that force is more than the maximum value of friction, then the object will start moving. Okay? No, it's not used in the using sense. So normal, the contact force has two components, as in it has two parts. One is friction and the other is normal reaction. Maximum friction remains the same as long as mu is the same and r is the same. If any one of these two things changes, then maximum value of friction changes. So if mu remains the same, if it's the same surfaces, and the reaction remains the same, if both of these things remain the same, F max is also going to remain the same. Otherwise, it might change from one part to the next. That can happen sometimes. Mostly, it will remain the same when mu and reaction are the same. In fact, it will always remain the same. In that case, if it is changing, then that would also change accordingly. Now, this is something that you will see in past papers as well. Sometimes they'll ask you to prove some inequalities. They'll ask you to prove some inequalities, show some inequalities. For example, if we've got something like this, what we have is a block of 7.5 Newton. It's at rest. That means it's in equilibrium. So we've got this force acting 7.5 Newton acting in the downward direction. And we have its components, this direction and this direction. We've got reaction. And the force that you are applying on this is acting in this direction. 7.2 Newton, you're applying a force in this direction, up the plane. Now, because of this force, they're saying the object remains at rest. It does not move. It does not move. Okay? It remains at rest. That means it's equilibrium. Now, if it is equilibrium, the opposite forces are supposed to be equal to each other. What are the forces that we've got? We've got 7.2 acting towards right. We've got reaction here. We've got weight component here. The other weight component is here. Now, first question is, where does friction act? You will have to check whether 7.2 is bigger or 7.5 sine alpha is bigger. In this case, we are given this value, given the value of tan alpha. We can use that to find sine alpha. I've done it here. If you have tan alpha given using a right angle triangle, you can figure out what sine alpha is, what cos alpha is. You would have to figure out which of these forces is bigger, 7.2 or 7.5 sine alpha. If 7.5 sine alpha is smaller, in this case that's smaller, and 7.2 is bigger, where does friction act? Friction is going to act opposite to that acts in this direction. And now, since we know the direction of friction, we just equate the opposite forces and we say, since it's equilibrium, opposite forces have to be equal to each other. So left forces equal right forces, upward forces equal downward forces, and that gives us the value of friction as 51/10, the value of reaction is 36/10. And now notice, we have to show this inequality. Mu is greater than or equal to 17/24. How can we show this? Remember, we talked about this. When we have equilibrium, in equilibrium, F is less than or equal to mu r. When you do not know whether the equilibrium is limiting or non-limiting, and you have to prove an inequality, F is less than or equal to mu r. F represents friction here. F is less than or equal to mu r in this case. So once you have the value for F, that's 51/10. Value for reaction, that's 36/5. Then we say F is less than or equal to mu r. Input values in this, and you get the result from that inequality that they wanted us to prove. So when you have equilibrium and they want you to prove an inequality, know that you would have to use F less than or equal to mu r. In the second case, they say, when the force acts down the plane, so now the force is acting in this direction, the block slides downwards because now it has the weight component acting in this direction as well, and the 7.2 Newton force acting in this direction as well. Friction is going to oppose that acts in this direction. Now they're saying it's sliding downwards. Show that mu is less than 31/24. Now, when the object is moving, when it's equilibrium, we know F is less than or equal to mu r. When the object is moving, the direction in which the object is moving, that is going to be the forces acting in that direction, they're going to be greater than the forces acting in the opposite direction. So forward forces, they will be greater than the backward forces when the object is moving. Now, if the object is sliding down in this direction, what that means is these forces have to be bigger than friction. That is when the object will slide downwards. So that's what we can use to find out another inequality in terms of mu. We can say, in this case, forces acting towards the left side, they should be greater than the forces acting towards the right side because the object is moving towards the left side. So 7.5 sine alpha plus 7.2, that should be greater than friction. Put F equal to mu r. Why? Because it's in motion. In motion, we know the value of friction is equal to mu r. Simplify this and you get an inequality in terms of mu. These forces are still going to be equal to each other. R and 7.5 cos alpha, they're always going to be equal to each other. Perpendicular forces on a surface, they're always equal. These two are always equal. But along the surface, since the object is moving down the plane, we say these forces are greater than friction. And that gives us that inequality. Mu is less than 31/24. So when you have to prove inequalities in equilibrium, F is equal to mu r. When an object is moving, you say the forward forces are greater than the backward forces. Forces acting in the direction of motion, they should be greater than the forces acting opposite to the motion. Is that okay? So in whatever direction forces the object is moving, forces acting in that direction have to be greater than the forces acting in the opposite direction. So basically, the idea is forward forces have to be greater than backward forces. Okay. In this case, forward direction is this direction. That's the left direction. That has to be greater than this direction. Okay. And that gives us the other inequality. Okay, let's move on. Now, sometimes what happens is they ask you to find something like this. Find the two values of T for which this is in limiting equilibrium. So we've got a set of forces here. We've got this force T acting here. And we've got weight, we've got friction, we have normal reaction. Okay. We've got these forces acting. And they're saying we've got weight acting here. That's 20 Newton. That's the weight. If we have a rough vertical rod, there's going to be friction because of that as well. And we have to find the two values of T for which the ring is in limiting equilibrium. Now, these are the forces that are acting. We've got tension acting in this direction. What are the components of tension going to be? One in the right direction, one in the upwards direction. Now, because of this tension having a component to the right side, there will be a normal reaction towards the left side, perpendicular to the surface. What about friction? Do we know the direction of friction? T sine 30 is acting in the upwards direction. 20 Newton is acting in the downward direction. Which one of them is bigger? We don't know. Because this is T, we don't know what that value is. If T sine 30 is bigger, then friction would act downwards. If T sine 30 is smaller, then the friction would act in the upwards direction. So direction of friction is not clear in this. And they're asking us to find the two values of T for which this is in limiting equilibrium. What does that mean? We will consider two cases here. One case in which the ring is in limiting equilibrium such that it's just about to move up the plane, move down the plane in this case. And the other case in which it's limiting equilibrium such that it's just about to move up the rod in the upwards direction. When it's about to move downwards, where does friction act? That acts upwards. When it's about to move upwards, friction acts downwards. So we consider these two cases and we find the value of T from that. And that gives us the two possible values of T, one in this case, the other in this case. These are the two values of T for which the ring will be in limiting equilibrium. Now, understanding the meaning of this is very important. The ring is in limiting equilibrium when T is equal to 68.5 Newton when it's just about to move up. It means if the force T was even slightly bigger than this, the ring will start moving upwards. The ring is in limiting equilibrium with a value of T equal to 28.3 Newton, and it's just about to move downwards in this first case. If the force acting, this force T, if it was even slightly smaller than this, the ring will start moving in the downward direction. So these are the extreme possible values of T that we have: 28.3, 68.5. If you have 28.3 Newton, you have limiting equilibrium with the ring just about to move down. If you have 68.5 Newton, you have limiting equilibrium with the ring just about to move up. Between these two values, if the tension is between these two values, between 28.3 and 68.5, in the middle region, the ring is going to be in equilibrium, but that's going to be non-limiting equilibrium. So whenever tension is between these two values, we are in equilibrium. Towards the left side here, the object will start moving downwards. Towards the right here, the object will start moving upwards. So these are the minimum and maximum possible values of T as well, for which the ring will remain in equilibrium. So this question comes in multiple forms. In this case, they're saying find the two values of T for which the ring is in limiting equilibrium. Sometimes they would say find the maximum possible value of T for which the ring will remain in equilibrium. In that case as well, you would consider the limiting equilibrium with the ring just about to move upwards. That will give you the maximum value. They'll ask you to find the least possible value of T for which the ring remains in equilibrium. You would say, in that case, the ring is just about to move downwards, and that will give you this case. So when you have to find greatest or least possible values of a force, in case of friction, you consider limiting equilibrium cases, and that will become clearer in this example as well, in the next examples. You have a very similar situation. You've got a set of forces, and they want you to find the set of possible values of a force P that is acting in this direction, such that the particle remains in equilibrium. Okay. Now, let's look at the forces that are acting. We've got weight acting downwards, 6 Newton. We've got 6 sine 25 acting in this direction, P Newton acting in this direction. Sorry, the components of weight, they are 6 sine 25, 6 cos 25. We've got P Newton acting here. We've got reaction acting here. Now, first of all, which direction does friction act in? We don't know, because that will depend on whether P is bigger or 6 sine 25 is bigger. Any of them could be bigger. We want to find the set of possible values of P for which the ring remains in equilibrium. We consider the extreme cases, the two extreme cases. One extreme case in which the ring is just about to move up the plane, and the other extreme case when the particle is just about to move down the plane. Those extreme cases. So we consider limiting equilibrium with the particle just about to move down the plane. We consider limiting equilibrium with the particle just about to move up the plane. We consider these two extreme cases. Those two extreme cases give us these values of P. One of them is going to be the maximum possible value of P, the other minimum possible value of P, and we say it's going to remain in equilibrium if P was between these two values. If P goes beyond these two values, then the equilibrium would break. Between these two values, as in this example, as I explained that to you here, between these two extreme values, the object is going to remain in equilibrium. This is the greatest possible value of P for which the particle remains in equilibrium. This is the least possible value of P for which the particle will remain in equilibrium. It's a very similar example to this. You can see that. Find the least possible value of P given that the particle remains in equilibrium. Again, we've got this force P acting in this direction. It has one component here, P cos theta, another component here. If we want to find the least possible value of P in this case, what does that mean? We say the P would be least if it's in limiting equilibrium with the particle just about to move down the plane. So that's what we consider limiting equilibrium with particle just about to move down, slide down. In that case, friction acts in the upwards direction. We equate the opposite forces and find the value of P from that. If we had to find the maximum possible value of P, we would say it's in limiting equilibrium with the particle just about to move up the plane. In that case, friction will act in this direction, and that will give you the maximum possible value of P. It's a very common question, repeated quite often in past papers. So whenever you have to find greatest or least values of any forces, and you have a rough surface having friction, consider using limiting equilibrium. One of those is going to give you the maximum possible value of that force. The other is going to give you the minimum possible value of that force. Okay, now, this is another case in which you're asked to find maximum or minimum possible value of a force. These are from recent papers, last examples that we're doing forces in equilibrium, and it turns out that it's taking a lot of time because I ended up going into a lot of detail. But it's okay, I think that should be helpful. So we have got this question now. It says the diagram shows a mass 10 kilograms suspended below a horizontal ceiling by two strings AC and BC. You can see that on the diagram, the block is in equilibrium. We've got some forces acting on this. We've got a force acting in this direction, that's F Newton. We've got another force acting downwards, that's 100 Newton. That's the weight of the object. And we've got the two tensions, one in this direction, the other in this direction. What I've done is I've just resolved the tensions and equated the opposite forces. In the first part, they said F is equal to 20. If the value of F is equal to 20, we need to find the tensions in each of the strings. What are the tensions going to be in each of the strings? How do you find them? You just resolve the forces, equate the opposite forces, and that gives you the result. In the second part, they ask you to find the greatest value of F for which the block remains in equilibrium in the position shown. Now, what does that mean? If this force F was to become too big, what would happen? The object is going to start moving towards the right side. And when it starts moving towards the right side, you're going to have a situation like this. The block moved towards right. The string on the right side here, this is going to become slack. It's no longer going to be taut. It's going to become slack. So in order to find that maximum value of F for which it will remain in equilibrium, after that, the equilibrium would break. Consider that cutoff point when this force becomes too big. It'll just about to be moving. It'll be just about to move upwards in this direction. The second string is going to become slack, so the tension in this is going to become 0. You'll put that equal to 0, T2 equal to 0, in the same equations. You have the same equations as before. Equate the opposite forces. It's just that the value of F is not 20 anymore. That was for the first part. You equate those opposite forces. And what you do is you put T2 equal to 0, because that would become slack if the force F was to become too big. You put T2 equal to 0, and that gives you the value for greatest F in this case. Okay, whenever a string becomes slack, tension always becomes 0. Yes. Similar to this, sometimes they can also ask you to find the least value of a force in a very similar situation. You have an object hanging from these two strings, and you've got a set of forces acting like this. And what happens is you have to find out the least value of X for which the block remains in equilibrium in this position. Now, think about it. If X becomes very small, you're looking for least value of X, right? If X becomes very small, what would happen? There would be no force keeping this object in its current position. Because of the weight, it's going to start moving downwards. It's going to start moving in this direction because of its weight. When that happens, the tension in the lower string, what is that going to become? How do you know which string becomes slack? Because it's going closer to this string, right? It's closer to this point. So the string's length will be longer, and the object will be closer to this point. So it will no longer be straight anymore. It will be slack. So when the object moves down, in this case, the lower string becomes slack. So what we do is we equate the opposite forces just like before, and we put T2 equal to 0. For X to be minimum, the lower string would have to have a tension of 0 because it would become slack, and that gives us the value of X, the least value of X, that turns out to be 86.6 Newton. Okay, so when, again, you have to find greatest and least possible values of forces when you have an object hanging from some strings. In this case, what you do is you put one of the tensions equal to 0. When you have a rough surface and limiting equilibrium, in that case, what you do is you consider limiting equilibrium. When you have an object hanging and you want to find the greatest or least value of a force so that the object remains in equilibrium, you put one of the tensions equal to 0, depending on which string will become slack. In the first case, if F was to become too big, the object will move in this direction, so this string will become slack. In the other case, the object was supposed to move in this direction. If X becomes very small, so the lower string will become slack. We put those tensions equal to 0, and that gives us the result. Okay, I hope that makes sense. I hope that was helpful. We will stop here. It ended up taking too much time, but that's okay. That's one topic. The other topic is kinematics. That's going to take time, and the rest of them will be fairly quick.